You know, there's something I get asked about all the time, and I always feel a little bad about my answer. Because the honest answer isn't very satisfying. And the question is just, why do magnets stick together? Now, you'd think that's an easy one. Everybody's played with magnets. Everybody's felt that. You push two of them together, and there's this invisible thing, this force that either pulls your hand in or shoves it back. And it's real. You can feel it. Your hand feels it. Your muscles feel it. And yet, there's nothing there. No string, no glue, just air. And this thing, this force just reaches right across the space between them. Now, here's the thing. When people ask me why, I know what they want. They want me to say something like, well, there's these little lines of force, and they come out of the North Pole, and they wrap around, and they go into the South Pole, and that's why. And I can draw that. I've drawn it many times, and it's not wrong exactly, but it doesn't actually answer the question. You see, that's just a description of what the field looks like. It's not telling you why. So let me back up a second, because I want to tell you something that my father taught me when I was very young. He used to take me for walks in the woods, and we'd see a bird, and he'd tell me the name in several languages. He'd say, in English, that's a brown-throated thrush. In Italian, it's this. In Japanese, it's that. In Chinese, it's something else. And then he'd say, now you know all those names, and you know nothing about the bird whatsoever. You see what he was getting at? Knowing the name of something is not the same as knowing the thing. And I think about that every time someone asks me about magnets. So, now, when you push two north poles together and feel that resistance, what's actually happening? Well, we say it's the electromagnetic force, and that's one of the four fundamental forces in nature. And the electromagnetic force is what holds the electrons to the nucleus of atoms. It's what keeps your hand from going through the table. It's what makes light. It's everywhere. It does everything. It's a truly fantastic thing. But here's the curious part. When you ask me why two magnets repel each other, I have to tell you it's because of the electromagnetic force between their electrons. All right, but then you ask, well, why do electrons repel each other? And I tell you, well, they exchange these things called photons, virtual photons, and that's how the force is carried. And then you say, well, why does that cause a force? Why does exchanging photons push things apart? And you know what? I can't answer that. I really can't. Not in terms of anything you're already familiar with. Because I don't understand it in terms of anything I'm familiar with either. And I've been thinking about this stuff for a long time. What I can tell you is that the theory that describes this, quantum electrodynamics, gives predictions that match experiment to 10 decimal places. 10 decimal places, that's like calculating the distance from Los Angeles to New York and being accurate to the thickness of a human hair. It's the most precisely verified theory in all of science. And yet when you ask what's really going on, what it means, we kind of shrug. The math works. The why is still a little mysterious. Now, the magnet itself. Why does a chunk of iron stick to your refrigerator when a chunk of wood doesn't? And this is where it gets genuinely interesting, I think. You see, every electron has this little property called spin. And it's called spin because when they first found it, they thought the electron was spinning like a tiny top, which it isn't, not really. But something is going on with it that behaves sort of like spinning, and it produces a tiny little magnetic field, a tiny one. From one electron, you'd never feel it. But here's what happens in iron. You've got all these atoms, and the electrons in them, under the right conditions, line up. They all point the same way. Now, you've got billions and billions of these tiny little fellows all pointing their little magnets in the same direction, and they add up. They add up to something you could hold in your hand and stick to your refrigerator. It's a collective thing, a cooperation of an almost unimaginable number of particles all doing the same thing at the same time. And I find that completely astonishing. That they do it spontaneously. You don't have to arrange them. Below a certain temperature, the iron just does it. The system finds that arrangement on its own because it's energetically favorable, which is a technical way of saying nature was lazy and found the lowest energy configuration, which I say with great affection because I think nature is wonderfully elegantly lazy. Now here's something that gets even more curious. If you heat a magnet up past a certain temperature, about 770 degrees Celsius for iron, called the Curie point, it stops being magnetic. All those nicely aligned electrons start jiggling around too much, too randomly, and the cooperation breaks down. The magnet it loses its magnetism. It's still iron. It's still the same atoms. But the collective behavior is gone. And then when it cools back down, they line up again. I remember once I was in a lab at Caltech and someone heated up this big chunk of iron right in front of me with a torch. And when it cooled back down and they brought a compass near it and the compass swiveled, I knew why it was happening. I could have written you the equations for it right there. And I still felt like I'd seen something remarkable. That's one of the things I like most about physics. Knowing why something happens doesn't make it less wonderful. In my experience, it makes it more wonderful. because now you see all the moving parts, all the little fellows cooperating, and it's even more astonishing that it works. So, why do magnets stick together? Because electrons have a property that acts like a tiny magnet. Because in certain materials, those tiny magnets line up and cooperate. Because that cooperation produces a field that reaches out through empty space and tugs on other magnets or on iron. Because fields carry force through some mechanism involving virtual particles that we understand mathematically, but not, I would say, philosophically. That's the answer. It's partial. It's a little unsatisfying in places. But I think that's more honest than telling you there are invisible lines of force coming out of the North Pole. The question of why the laws are what they are, why electrons have spin, why virtual photons carry force, why any of this is the way it is and not some other way, that one I don't have. Nobody has. And I'll tell you something, I find that more exciting than frustrating, because it means there's still something to find out.